Welcome back, everybody. We're going to be talking about centripetal acceleration, and I'm going to try to get rid of the misconception that people have about centripetal acceleration or acceleration in general. So the first thing we're going to start off with is actually Newton's first law. And what Newton's first law states is basically says two different things. An object in motion will stay in motion unless a force acts upon the object. An object at rest will remain at rest unless a force acts upon the object. So the first part of the statement is what we're going to be looking at today, and we're going to use this to understand the idea of centripetal acceleration. So it says if we take any object, so let's draw this little particle, and it's in motion, let's say it's going along this way towards the right, it would follow a trajectory that is straight or linear, and it will continue to follow this trajectory until an unbalanced force will act upon it. We're assuming that there's no forces acting on the particle as of now, but let's say if we do put a force in this direction, it might cause an object to slow down and actually reverse direction because there is an unbalanced force acting upon it. But if there is no force being acted upon the object, then it will continue to follow this path towards infinity. Now, we don't see that in our everyday case because, again, in the real world, there's a lot of forces acting on various objects at any given moment of time, so we don't really see this phenomenon. But this is actually what goes on fundamentally in nature. So we're going to abstract this a little bit further, and we're going to draw a circle. So let's assume that a particle is going around in a circle, and instead of it accelerating with its speed, we're going to say it's going to have a constant speed. So what I'm saying is that the velocity, it has some velocity, but its magnitude, the magnitude of the velocity is actually constant. And what's special about this implies that there's no acceleration on the object, at least in the tangential direction. And also I'm going to define this radius of this circle. This is going to be r. So going back to Newton's first law, it says that an object will remain on a linear trajectory if there's no force acting upon it. But if you look at this picture, we say that the particle or this object is actually moving at a constant speed, but its path is actually changing, and there doesn't seem to be any forces acting upon it. However, the particle is actually changing direction over the given amount of time. So what that must mean is there must be some sort of force or some sort of acceleration that is causing this object to change direction. So if we look at this previous example that I drew, the object will remain going in this general direction. If it starts turning or changing direction, there must be some sort of force or some sort of acceleration acting on the object to make it change that direction. So if we look at Newton's second law, just imagine there's a force right there. If we look at Newton's second law, we have this idea of F equals ma. So if we go back to this picture right here, that must mean this object, although it has a constant speed tangentially, it does still have acceleration. And its acceleration vector actually points towards the center of this circle. So this is called centripetal acceleration. So what I'm basically saying is that if you take some time later, we're going to have the same velocity just in a different direction. However, it's also going to have some sort of acceleration tied along with it. So this acceleration vector is actually causing this object to change direction over time. So to put that more in a mathematical statement, what we're saying is that although it has a constant velocity in terms of its magnitude, let's define this as t equals, or t naught, and define this as t final. So I'm saying that the velocity of the magnitude at t naught is equal to the velocity of the magnitude at t final. However, the velocity vectors at t naught does not equal the velocity vector at t final. The fundamental thing to get from this is that although the object has a constant speed, it still has acceleration, and that's simply because the path is changing over time. And that just means that the velocity vector changes from a vertical direction to a sideways direction or any other direction that is drawn tangentially to this curve. Now that we understand that, we can abstract this idea or extrapolate this idea a little bit further so we can apply it to dynamics. So let's take a particle, for example, and this was actually a very specific case because this is going on a circular path, which is very specific. But let's say a particle can move in an arbitrary direction along a path, so it's going along this direction. What we want to do is actually define the acceleration at any given point, or at least the centripetal acceleration. And to do that, what we can do is actually imagine at each given point along the path, we can draw this tangent circle to the path. And at that given moment, it will be defined by this idea of this radius of curvature, and the centripetal acceleration at that point will be dependent on that radius of curvature. And you can see that this circle changes over time. So if you look at the point right here, the circle may be a little bit larger than it was prior, and this will be this other radius of curvature, and the centripetal acceleration will also point in that direction. So you actually could define the centripetal acceleration of any given path by looking at the radius of curvature at any given point. And again, this is fundamental to what we said earlier. If the object can be said to have a constant speed, but however, if the path is changing over time, it does have acceleration, and it has acceleration in terms of this idea of centripetal acceleration. And one thing to point out is that the curve changes concavity as you go from one state to another. And if you look at the circles are always within the concavity of the path. And that's simply because the centripetal acceleration points in the direction that the path changes towards. So since this object is moving in this general direction, the centripetal acceleration will point downward because the object is moving downward over time. And the same can be said over here. So it's being turned upward, so the centripetal acceleration will be pointing upward. And that is why the radius of curvatures, or the circles of radius of curvatures, point within the concavity of the path. So I found this little program that demonstrates what I've been talking about, this idea of the radius of curvature, and we could use this to find centripetal acceleration. So this little program demonstrates what I'm saying. So we could take this path and move this particle along this path, and you can see that at any given point, there can be this tangent circle with some given radius that could tell us this idea of centripetal acceleration. As the path changes concavity, the circle also changes concavity. And if you want to see this demonstration and play with this on your own, I'll leave a link in the description down below. This was made by Interactive Mathematics, and I'll leave a link in the description so you guys could mess with this. But this is the very basic concept of what is basically going on with centripetal acceleration. So I just wanted to write out the concept that I've been trying to tell you guys throughout this video, and that is, if an object follows a path that is changing over time, then the object must be accelerating, regardless of having a constant speed. That doesn't mean that only particles with constant speed have centripetal acceleration. The object can have acceleration tangentially, as well as acceleration normally, or in the centripetal direction. But if the object is moving at a constant speed and the path is changing, it does have a component of acceleration. It may not have a tangential component, but it does have a centripetal component. And that is a crucial concept to understand when solving dynamics problems. So hopefully this helped you clear up some misconceptions about acceleration, and I'll see you in the next video.